Oh, people are just loud?
Yes.
You can't hear me. Now can you hear me? All right, you hold it and I'll read.
Yes.
Okay, welcome to the best paper session. We're getting near the end of the main conference. And before we move into the best papers, we're going to give out 2 awards for best demos. So the best system demo runner-up, it's like a beauty pageant, is Compare MT, a tool for holistic comparison of language generation systems. And if you are an author of this demo, you should come up now while I'm reading all of your names. Graham Neubig, Ji Dao, I would get everybody wrong, apologies. Junji Hu, Paul Michael, Danish Pruthi, and Jinyi Wang. Anybody want to come up and take certificates? Marvelous. Congratulations. Okay, and the best system demo is enabling search and collaborative assembly of causal interactions extracted from multilingual and multi-domain free text. George Barbosa, Zechi Wong, Gus Han Powell, Dane Bell, Rebecca Sharp, Marco Valenzuela Escarcega, and Mihai Soriano. Anybody? Yes, excellent. Congratulations. He's taking all of them? Okay, and moving on to the Best Paper Awards, Best Talk Paper Awards.
Best explainable.
We have first the Best Explainable NLP paper, which, where? There they are. CNM, the title was up there, an interpretable complex valued network for matching. Kichi Lee, Benyu Wong, and Massimo Melucci. Congratulations. And just to explain, we'll do award talk. So
we'll let them get
We'll let them give their talk.
Sorry, the speaker doesn't work. Can you hear me? Oh, okay, good. So thank you very much, and sorry for delaying. So it's my great honor to be here to present our work. So my name is Xiushi Li, and I'm a second-year PhD student from the University of Padua. And actually, this work is a joint work with my colleague Benyu Wang and our supervisor Massimo Melucci. And actually, Benyu and I share equal contributions to this work. And we would like to thank the CAUSE project to fund this research. Where CAUSE is a European Union Marie Curie research project, and all the 3 authors are involved in this project. So basically what we do here in this work is to build a neural network for matching, but it's sort of different from the classical neural network in that it is sort of interpretable with complex valued, constrained components, and so that the network is sort of interpretable. It can be explained as concrete physical concepts, basically concepts in quantum theory. So as we all know, neural networks have achieved significant breakthroughs in the natural language processing domain. But one of the major issues facing those neural networks is the interpretability issue. So in a very recent survey paper by the Zachary Lipton in 2016, an interpretable model has 2 main important properties, basically transparency and post-hoc explainability. So basically transparency means that the components are sort of explainable in design phase right before the model is deployed to a real task. Whereas post-hoc explainability is concerned about the explanations of why the model works after it has been deployed to a real task. So actually many existing works have addressed this post-hoc explainability issue by giving visualizations of the model components or providing textual explanations of why the model works. But the transparency issue is seldom addressed. So in this paper, what we do here is to address the interpretability issue for natural language processing models, and we basically seek to build a model that is sort of transparent and post-hoc explainable at the same time. So our motivation stems from the very earlier works made mainly by Diederik Eltz and Peter Burza on the non-classical phenomena in human language understanding. So basically, those studies demonstrated that quantum theory, which was originally proposed to describe the behavior of particles in the microscopic level, is actually beneficial to model the inherent uncertainties in human language, especially the word meanings and the word semantic combinations. So this provides us with the theoretical inspirations to give a quantum interpretation of the human language understanding. So in theory, if we can build an applicable model on the basis of the theoretical framework, the model is sort of transparent. It has a very natural advantage of being transparent because the components could be readily explained as concrete concepts in quantum theory. So actually, we are not the first to recognize this point. Actually, there are already existing works that are trying to seek inspirations from quantum theory and to build applicable models for natural language processing or information retrieval tasks. Apart from the limitations in the performance or effectiveness, those works are not theoretically sound enough in that they are either not fully quantum-inspired frameworks or the implementation is based on real values, whereas complex values are actually crucial to formulate the concepts of quantum theory. So that is why we focus on building this novel framework which provides a unified quantum view of different levels of linguistic units basically on unified semantic Hilbert space. And the implementation of such a theoretical framework is an end-to-end complex valued network for text matching. So basically, this network is sort of transparent in that we add numerical constraints to the complex value components to ensure that those components could be explained as concrete concepts in quantum theory. So basically, they are either states or the probability values. Before we move into our model, I would like to spend a couple of minutes briefly explaining the preliminary knowledge of quantum theory. So basically, the quantum theory is defined in a Hilbert space, which was infinitely dimensional inner product space. But in practice, it is often simplified to a complex vector space with finite dimensionality. So a pure state is used to describe the state of a quantum particle. So it can be either a basis state if it corresponds to a basis vector or a superposition state otherwise. So in either cases, pure state is mathematically represented as a unit-node vector with complex coefficients. Mixed state is used to describe the classical mixture of a set of quantum particles. So basically, you have a set of quantum particles, and you have the corresponding classical probability distribution of these particles, and you're going to mix them together into a mixed state. And this mixed state is mathematically represented as a density matrix, which is complex valued, and it is positive semi-definite with unitary trace. The measurement is introduced to measure the state of an unknown quantum system here. So basically, it involves the set of mutually orthogonal unit-node vectors, and they form a complete basis of the Hilbert space. So after the measurement, the system will collapse onto one of the measurement states, and the probabilities form a classical probability distribution. So if you take a look at the example of the two-dimensional case here, the system rho will, in probability P1, collapse onto the state of V1, and in probability P2, collapse onto the state of V2, where P1 and P2 sum up to 1. And the P1 and P2 correspond to the square of the length of the yellow line segment yellow line segments respectively. So with that preliminary knowledge in mind, we basically introduced this analogy between the uncertainty in language and the quantum theory. So basically, a single word may have different meanings in different contexts. And this is quite similar to the uncertainty of a pure state, which can basically collapse onto different measurement states by the quantum measurement. So in theory, if we are able to use different measurement states to represent different meanings of a word, then even a single pure state can in theory be used to encode multiple meanings. On the other hand, the multiple words may be semantically combined in different manners under different contexts as well. So if you take a look at the case of the ivory tower, so in the left-hand case, it is just an addition of the meaning of the individual words, whereas on the right-hand case, another new meaning emerges, which is some sort of different from the individual, which is sort of different from the individual word meanings. So actually, this case is quite similar to the uncertainty of a mixed state, whereas if we use the density matrix to represent the mixed state, it actually corresponds to many different possible probability distributions for a same set of quantum particles here. So in theory, if we use a quantum particle to represent the word, then this density matrix can be used to represent the multiple ways of semantic combination of those words. So based on those analogy or this similarity in between the uncertainty of human language understanding and this quantum and the uncertainty in quantum theory, we basically build such a semantic Hilbert space which formulates different semantic units on the same space. So basically, the words are regarded as pure states or basically superposition states, and the word semantic combination is formulated as a mixed state, which is a classical mixture of words. And then we introduce a set of semantic measurements to extract the high-level semantic features of the set of words here, and the final result is a probability vector, and each corresponding to a semantic measurements, and this vector is the high-level semantic representation of this set of words here. So it is worth noting that this semantic measurement is sort of different from the quantum measurements in that they are not orthogonal to each other, but we basically keep them trainable so that we are able to learn this discriminative semantic measurements in a data-driven manner. And basically, this theoretical framework is applied, it's implemented into a model for text matching problem. The problem is to select the most accurate answer to a question. So it requires the computation of the similarity of a pair of question and answer, and you're going to rank the answer according to the similarity values with respect to a question. So the reason why we apply this to the text matching problem is that we find it beneficial. We find it potentially beneficial to capture this matched local context between the question and answer. So if you take a look at this case here, so the woman's role change during the war is semantically matched. It's semantically similar to the walls to the local context of war study, the new era for women's opportunities, which basically determines that the answer is the most suitable one for the question. So in theory, in our framework, we are able to identify those local contexts and model those two contexts as density matrices. And we're going to use a set of trainable measurements that basically gives the very similar measurement results to both density matrices and correctly match the answer with the question. So this is the architecture of our proposed network, which is the complex value network for matching. So basically, it starts with a complex valued embedding layer where you have a very large lookup table of complex vectors. And then we introduced what we call a local mixture strategy, which identifies a set of local context from both the question and answer. So this is a very flexible approach where you can freely determine the location of the context and the length of the local context. I mean the number of words in the context. For example, you can determine many different context lengths for the question and answer, and you're going to apply a sliding window throughout the sentence, and you finally obtain a set of density matrices for both the question and answer. And they are basically passed to a same set of semantic, they're passed to the same set of trainable semantic measurements, and the obtained probability values are assembled together and passed to a pooling layer, which is a global pooling, because we want to identify the most prominent local context corresponding to each semantic measurement. So as a result, what we obtained is actually a probability vector representation for both the question and answer, where each value corresponds to the most prominent local context for one semantic measurement. And this vector-based matrix is used to determine the similarity value between the question and answer. So actually, this is an end-to-end training process but the only parameters we learned are the density matrices of the corresponding to the semantic measurements, and also this complex value word embeddings. And they can be learned in following this backpropagation algorithm. So we basically evaluate our models on TrackQA and WikiQA, and it turns out that we are able to get very comparable performances to very strong baselines. And in particular, we also outperformed an existing quantum-inspired question answering model, which was proposed very recently in 2018, and it is regarded as the state-of-the-art quantum-inspired question answering model. We also conducted an ablation study trying to check the performance, trying to check whether each component brings positive impact to the final performance, and we basically got positive results that all the three components do bring positive influence to the final performance. And we also analyzed the transparency of our network by comparing our model with the deep neural network in terms of the physical meanings and constraints. And it shows that our model is well constrained with complex value representation for the components, and those components can be mapped to concrete physical meanings, whereas the traditional convolutional neural network or current neural network does not have numerical constraints on the cells, and so that they could be hardly understood by human beings. And we also conducted a series of post-hoc explainability analysis where we visualized this. One of the most interesting findings is that when we visualize the match patterns of the question and answer, we're not only able to identify the matched cases where the question and answer share very common crucial terms, but we are also able to match the cases where they don't share many common terms, but they are but they share very similar meanings. So this means we have a pretty good reason explaining why our model works. So to wrap up, so we have addressed this interpretability issue for language understanding, and we basically built a complex value neural network for matching inspired by the quantum theory. So this network has been demonstrated transparent and post-hoc explainable, and this is not at a great sacrifice to the final performance, meaning we are still able to achieve comparable performances to strong CNN and LSTM baselines. So for future work, it will be interesting to see the quantitative analysis of the interpretability. So it would be ideal if some metrics could be designed to measure to what extent our model is interpretable, so that it could be compared with the other models in a fair manner. And also what we are working on is to incorporate our model with the state-of-the-art neural networks for question answering, and also we are working on larger tasks with more complicated question answering tasks. So for example, this common sense question answering that's going to appear later. And that's it. Thanks for listening.
We have time for one question. Short. Oh, wait, I hear a short question in the back.
It's very short. Emily Bender, University of Washington. What languages did you test this on?
English.
Thank you.
Thank you. Thank you for listening.
All right. Next speaker